Hi, welcome. Today we're going to be talking about ANOVA, analysis of variance. Let's look at our first screen. A one-way ANOVA is actually an extension of a two-sample t-test. The objectives of ANOVA are to estimate treatment means, differences of the means, and then test a hypothesis to see if there's a statistically significant difference between any of the means. A two-sample t-test allowed us to compare between two population means, but we want to expand this test so that we can look at more than two populations. We could perform several pairwise comparisons, such as mu1 equals mu2, mu1 equals mu3, mu2 equals mu3, but the probability of falsely rejecting at least one hypothesis increases as the number of t-tests increase. So what we'd really like to do here is come up with one test that's going to let us test across all of our population means. So let's go to our next slide. What we're going to use here is two estimates of the population variance. The first estimate is called the S squared W, or the within variance. This is an unbiased estimate of sigma squared, the population squared. It represents the pooled estimate of a common variance. Notice how we use the sample size and sample variance of each of our samples for each of our populations. This estimate of sigma squared is unbiased whether or not the null hypothesis is true. Another estimate of sigma squared that we're going to use is the between variance, the S squared B. This is also an unbiased estimate of the common variance, but only if the null hypothesis is true. It estimates the common variance by looking at each sample mean away from the grand mean. We're going to use these two estimates, S squared W and S squared B, to come up with an F-test. This F-test is going to allow us to have a test statistic. We're going to use the ratio of the S squared B over the S squared W to be a test statistic for us to test our null hypothesis, that mu1 is equal to mu2 is equal to mu3, up to as many population means as we're including in our test. This test statistic follows the F distribution. As we see in this slide, this test statistic is going to allow us to evaluate the null hypothesis. The 2 degrees of freedom associated with the F distribution are degrees of freedom 1, that has k minus 1 degrees of freedom, k being the total number of populations, and the second degrees of freedom, n minus k, where n is the total number of observations. The overall F-test looks at the null hypothesis. Are the means equal to each other? The question we're asking, the alternative hypothesis, is that at least one of these treatment means is significantly different, just one. Now, to do this, we need a way to control that experiment-wise error. Now, there's a lot of ways to do multiple comparisons in ANOVA. I'm only going to be using one way. I'm going to be using Tukey's method. Tukey's method allows us to control the experiment-wise error while we test to see the differences between our treatment means, between our population means. So there are many other ways out there, and you need to find the most appropriate way for your analysis. But in this work today, we're going to be using Tukey's. I'm also going to be using Minitab software to run the analysis. This slide shows you what the overall F-test, the null and alternative hypothesis, look like. Again, the question we're asking is, at least one of the means are different. This is the first output you're going to see. It's called an Anova table. This Anova table computes the sums of squares. The differences it partitions out the variation in 3 different ways. If you look, here's the sums of squares of our treatment. This is actually the sum of the square difference of each treatment mean and the grand mean times each sample size. The next one in our Anova table, the sum of the squared errors, is the sum of the square difference of each observation and its treatment mean over all treatments. And then the total, the sums of squares of the total, is simply the addition of the SSTR and the SSE. It's the sum of the square differences between each observation and the grand mean over all the treatments. Now notice here, the MSE. This is the mean sum of the squares for the error. This is simply our SSE divided by degrees of freedom. This value is the best unbiased estimate of population variance. Remember, this is our S squared W. It's unbiased whether or not the null hypothesis is true. The MSTR is that estimate between the S squared B. We take the ratio of these 2 values to get our test statistic, our F test. When the null hypothesis is rejected, when our p-value is less than our level of significance from our Anova table, we know that we can reject the null hypothesis. One of those means is significantly different from another one. So this is where Tukey's comes in. Tukey's method allows us to look at the multiple comparisons and determine which treatment means are different now that we have rejected the null hypothesis. So let's go to the next slide. This slide has our problem for the day. A forester is working with an uneven-aged northern hardwood stand, and he wants to know, is there a significant difference in mean saw timber volume in cubic meters per hectare produced from the stands using 3 different methods of selection system? So in this data set, we have 3 treatments, 3 populations. We have samples from each of these, and we want to test to see if our means are different. On the next slide, you're going to see the actual raw data from the 21 stands. Our inference will be assessed using an alpha of 0.05. Here's the data. Notice that I have it listed by stand, method, and then volume. This is our response variable. This is what we measured. So we have 3 treatments, 3 different populations, and we've measured the volume from each of these different treatments. When you enter this in Minitab, you're just going to have 3 columns. You're going to stack all of your data. This next slide shows you the steps in Minitab to get you to a one-way Anova. You are going to select Stat, Anova, and then one way. Notice that in the response box, you want to put volume. That's what we called our response variable. And in the method, we're going to put method in the factor box because method is how we described treatment. Now you want to click comparisons. This is where we set up for our Tukey's family error rate. We're going to enter 5%. This is setting up our level of significance for our family of pairwise comparisons. You're then going to simply click OK and OK. So let's look at the Anova table. Let's see what the output is telling us. Remember, the null hypothesis is that there is no difference between these 3 selection system treatments in terms of mean saw timber volume. So the Anova table, what we're going to look at now, shows us the output. We see here our factor is our treatment. You look across and you see the p-value. This is the answer to the question we're asking, our hypothesis test. Is there a significant difference between the mean treatments? Remember the decision rule. If the p-value is less than alpha, We're going to reject the null hypothesis. In this case, our p-value is very, very small. Minitab stops after 3 decimal places, so this p-value is probably something like 0.0001. The p-value is less than alpha, or 0.05. We're going to reject the null hypothesis. Because we have rejected the null hypothesis, we now know that at least one of these treatment means is different. So the next set of output from Minitab is going to tell us which ones are different. So let's look at the next part of the output. This grouping information uses Tukey's method. What we see here is that means that do not share a letter are significantly different. It also gives you the average for each treatment, method 1, method 2, and method 3. What this output is telling you is that there is no statistically significant difference between method 1 and method 2. Even though the means are mathematically different, there is no statistically significant difference between the mean volume for these two treatments. However, method 3 is significantly different from both method 1 and 2. It's lower. It's producing a statistically lower amount of volume from this method. So now that we know we have different treatment means, Minitab also gives one more bit of information. It constructs confidence intervals about the difference of all of these comparisons. Now the basic rule when looking at these two sample confidence intervals is that if 0 exists within our confidence interval, we have no significant difference. Now we already know that method 3 is significantly lower than method 1 and 2. But what the confidence interval does is it tells us how much. It gives us an estimate of how different. So let's look at that output right now. We're looking at simultaneous confidence intervals. Remember, our level of significance was 5%. So Tukey's is constructing 95% simultaneous confidence intervals. But here, look right here, 98% confidence level for these individual tests. This is exactly where Tukey's is controlling the experiment-wise error. It's adjusting our level of significance for all of these multiple comparisons. So let's look at this first one. This says method 1 subtracted from method 2. So 2 minus 1. Here is our confidence interval. It goes from negative 9.044 to positive 0.702. This is a 0 exists within this confidence interval, telling us there's no significant difference between method 1 and method 2. But in this next one, method 3 minus method 1, it goes from negative to negative values, our lower limit and upper limit. We have all negative values in our confidence interval. This tells us that not only is method 3 significantly lower than method 1, but that the value, the difference of these two treatment means ranges from 14.244 to 4.498. Method 3 produces this much less volume. I hope this analysis and this stepping through this problem in Minitab, this one-way ANOVA, will help you with your further analysis. Thanks for joining me today, and have a nice day.